Alright everyone, welcome back to our episode 13 of the number series. For today's video, we will be doing the exercises at chapter 13 about numbers in other bases. Question number 1, write 1492 in base 2, 3, 7, 9, and 11. And first I'm going to show the result, and then I'm going to do an example at the back of the page. Okay, let's say we want to convert this number to base 2. First, we take the number and we take the remainder of modulo 2, which is 0, and we divide this number by 2, and we take the remainder and divide that number by 2. The remainder equals to 0, and now we take the remainder of 1 and divide it by 2, and we get 1 as remainder, and we just keep repeating this process until at the end we get the number 1, and we take the remainder and equals to 1. How it works is that we just keep dividing and make the number smaller and smaller. Those number 1s that we are splitting out is going to form this binary number here. And that's basically how it works. And this is the example of base 3. First, we take the remainder of 1 and divide these numbers minus 1. We're gonna minus 1 and divide this number by 3. We take the remainder of 2 and divide the new number by 3 and divide it by 3. Okay, take the remainder of 1 and divide that number by 3. Okay, just keep repeating this process. Okay, and that's how we convert the number into different bases. And just check your work. The same thing for question number 2. We just have a different number and we're still going to convert number into other bases. And questions 3 and 4 asking us to convert the number back to base 10. Well, this one is just doing things backwards because we begin with the larger digits, and we take that number, multiply by 5, and plus this one, multiply by 5, plus 1, multiply by 5, and we just keep doing this process. And you will notice that the number that we begin with will get multiplied 5 by the process, and this 1 will be multiplied 2 times, and this 4 will be multiplied 1 times, and 1 will not be multiplied by 5, and that's how we get the numbers. And this is just one more example of expanding this number here. And yeah, just check your answers. Okay, and question number 5, solve for x. Okay, it's not very clear. Let me focus the camera. Okay, so we're gonna convert those two numbers which is not in base 10 in other bases and convert them into a different bases. We first convert them into the base 10, then we convert it into the base that we are required it to convert to, and like this we convert this. Okay, this is the answer, and yeah, like this one we first converted to base 10, and then we convert the base 10 version to the base 5. Okay, this is an interesting question. So 1, 2, 3 base x equals to 1002 base 4. So for this problem, we rewrite the 123 into this form, and we have 63 in base 10, and we factor it and find that x is the only solution. Question 6. Okay, it's just very similar. So for the first two questions, the first one, this is the answer, and the second one doesn't have a solution. And this one is missing 2 digits, And after you expand it, you will find those two relationships, and you gonna simplify it, and you reach out that x equals to 1. And question number 7 and 8, we're gonna construct a multiplication table for base 7 and base 8. Well, it's very boring. You just multiply those two numbers and make a table, and I'm not going to create a very large table because it is very time consuming and it's not interesting, and there's not a lot of skills inside, so that's all about it. And let's talking about question number 9. Those numbers are in base 9, and we're gonna perform addition, subtraction, multiplication, and division. No, this is still multiplication, sorry. So division, I think it's the next chapter, so don't worry about that for now. And I think it's fairly simple, but like when you are doing the subtraction, you borrow from the previous digit and you get a number of 12, right? And that's one thing to keep in mind. And when you are adding those numbers up, only push 1 to the next digit only if it has the 12, not 10 anymore, okay? How you do multiplication is like for example, this one, I'm gonna 2 times 42, and I move those digits. This one, for example, is in the unit digit. I move it to here, 2 times 2, and this one 4. I move it to the 10th digit, and I got 2 times 4, and the 1. I'm gonna move the 42 here, and I'm gonna perform the addition, and I got this number. Well, how it works is that if you write it in form like this, and you're gonna realize that the first digit, or like the first largest digit of the two numbers, they combine, they're gonna have a factor of 9 to the power of 2, and that's going to be this digit here, and like 1 times 2 and this 2 times 4, you're gonna have the 10th digit over here, and the last one is the unit digit. You multiply those two and it's going to be the unit digit. Okay. Well, very simple and very similar. You just 2 times this one here, and 5 times this one, and 1 times this, and then you add them together, and I hope that's not a big problem for you. If it is, well, don't worry, it's not that difficult, okay? Just do some studies, and I believe you'll get there eventually. So, question 10, we have similar instruction in problem 9, so I'm just going to show the result to not be repetitive, because I don't want it to become a very lengthy video. And question 11, let D1, D2, D3 stand for this, and we have to evaluate those expressions here. We need to evaluate them as rational number in base 10. Okay, how are we going to do this is, if this is a limited amount of digits, we can simply combine them together, like 2 to the 2 over 7 and 5 over 49, and we combine them together, we get this fraction. And similarly, okay, this one is a little different because this is infinite. And how we're gonna deal with this is, first we're gonna try to cancel out the infinite parts, and I multiply this number by 7, which push all the digits to the left by 1 place, and I'm gonna subtract the original one, and I get rid of all of the decimal, and I'm gonna have a 3 in the base 7, and since 3 in base 7 is equivalent to 3 in base 10. And I can just rewrite it like this. And I divide this 3 over here by the number 6, and I got 1 over 2 equals to 0.5, okay? And similarly, this one is just the same process, except it has 2 repetitive digits in a period, and we're gonna multiply 47 to push this number to the left by 2 places, and we get this fraction. And the grade question 12 is just the same type of problem, and just check your work, alright? This is the answer. And question 13, in which base b is 1111 divisible by 5? So if we make a table about all of the value of b, that's all of the least residual of b modulo 5, we'll find that those are divisible by 5. So question 14 shows that those are even numbers. So we prove that we take the modulo 2 over here, and so because this is in base 7, and we take the remainder of 7, we will find this is equal to 1, and if this number is odd or even, it's just depending on the number itself. If this is even, then it's even. If this is odd, then it's odd. And yeah, the whole thing, the oddity is going to depending on the sum of the digit, which we know that the sum of the digits of those numbers is always equal to 6. So those numbers are indeed even number. And part B, and the part B is just what we proved in part A, the sum of the digits. And part C, in which other basis, if it's true that if an integer is even, then any permutation of its digits is also even. Well, for all the bases, because this is all the base, and we take the modulo of 2, and we have the remainder of 1. And we can have the expression of the sum of the digit. Okay, question 15. So, an eccentric philanthropist undertaken to give away $100,000. Huge. He is rich. Okay, he is eccentric because he insisted that each of his gifts must be a number of dollars. That's a power of 2, and he will give no more than 1 gift of any amount. How does he distribute his money? So this question is just asking us to convert this number into base 2, and each transaction is just going to be 2 to the power 2 to sum of the power, and here, like, this is the result. And the question 16 proves that every positive integer can be written in unique form of n equals to e of 0 plus 3e to the 1. Well, it's basically in base 3, except each digit could only be -1, 0, or 1. And a simple way to understand it is that we know each number has its unique expression in base 3, and we keep replacing e of I. For all of e of I equals to 2, we replace e of I equals to -1 and replace the next digit. We add the next digit by 1, and this is just an example how you're going to do this. For example, this is the base 3 expression, and we change those two digits have the number 2. We replace it with -1, and the next digit we plus 1. And yeah, we just keep doing this until there's no digits equals to 2. And we know that the number is just going to be a limited amount of size, and we will always reach the end of the expression. Yeah, when doing this a few times, this because it's not going to be infinitely big, and there will be a time that we have to stop and finish the process. And this problem is also provable using induction, and this is basically the proof that, like, you suppose nk is available for be represented by this range, and you're gonna separate the three range after having an extra digit, and you're gonna combine them and find that this is the next requirement, and that's how you're gonna prove it. And don't forget that the base has to be exist for the induction to be true. Question 17. So the hexadecimal notation in base 16 use the digits A, B, C, D, E, F for those numbers here. We'll convert those to different bases and convert them into hexadecimal. And part B, we're gonna convert the hexadecimal back to base 10. Well, these are the numbers here. Well, we already talked about how to convert numbers into different bases in question 1 and 2, and how to convert them back into base 10 in question 3 and 4, and not going to repeat that again. And part C, is there any longer words than this? Well, I don't know. Maybe there are. Well, at least not for what I know. So if you find one, well, you could share this in the comment, I guess. Well, I don't know if there's any word longer than this. So question 18, converting decimal to binary. It is convenient to first convert this to octal and then replace each octal digit with its binary representation. For example, we got okay. Well, we need to explain why does it generally work, because you can expand in the octal digits to three different digits in binary, and it is interchangeable, and it's kind of convenient, but not that really. So yeah, I think that's how it works. So question 19. So another way to represent a number is using factorial notations, and this notation is going to be 1 factorial, 2 factorial, 3 factorial, and keep going. And we're gonna write those numbers in base 10 and convert those numbers into factorial notation. Well, this is the answer. And we need to prove that every positive integer have a unique representation in factorial notation. Well, this can also be proved by the induction, and this is going to be your assumption, and you're gonna find that it is indeed, okay, this is going to be your assumption, and you're gonna find that it is indeed true. It is indeed true. So question 20, find the base b in which 45 base b and 55 base b are both squares of consecutive integers. Well, suppose 4b plus 5 equals to n squared and 5b plus 5 equals to n plus 1 squared. So we can try to cancel out the b over here, and we get this expression here, and we factor it, and we get a value of n, and we will find that b equals to 19 is the only solution. Well, that concludes our section today, and I hope you enjoyed the video, and see you in the next one. Bye. Oh, where's my mouse cursor? Okay, here we are.